All right, so I'm going to go through this free response question from the 2016 exam. So it gives you this reaction, and this is showing the dissociation of phenol, which is a weak acid, in water. And so it asks you to determine the pH. And so this is not as easy as just plugging in 0.75 to the negative log because this is a weak acid. And so I've got to show the weak acid dissociation reaction here, which is right above. I'm going to create an ice chart. My initial concentration of my weak acid is 0.75 molar, 0 and 0 for the conjugate base and hydronium ion. Okay. If you just did the weak acid producing its conjugate base plus H+, that's totally fine. That is a valid reaction as well. My change is minus X plus X plus X, and so at equilibrium I have these concentrations. I'm going to put this into my equilibrium expression for my Ka value. So I've got x squared over, because it's x times x, over 0.75 minus x equals my Ka, and the Ka was given to you up above. Now, I don't want to have to deal with this minus x because then that would mean that I would have to use my quadratic formula. And so what I do is I can actually get rid of it because this passes the rule of 100. Specifically, since your Ka is so small, we can assume that any x value you would get is going to be so tiny that it's not really going to affect your initial concentration. So we'll get rid of this minus x, and then we'll solve for x. So ultimately, the x that I got was 9.2 times 10 to the negative 6th, which is your concentration of your hydronium ion. So if you showed this setup and you got the correct H+, you got a point. The next step, all you have to do is take this concentration of hydronium ion and take the negative log of it to get your pH. So you got another point if you got the correct pH. Now keep in mind, since the values that are given to you have 3 and 2 sig figs, that means you should have 2 sig figs for your final answer, which means your pH should have 2 decimal places, which is why I put 5.04. All right, for B, it says for a certain reaction involving this acid to proceed at a significant rate, the phenol must be primarily in its deprotonated form, meaning you should have mostly just its weak conjugate base. In order to ensure that it's deprotonated, the reaction must be conducted in a buffer solution. On the number scale below, circle each pH for which more than 50% of the phenol molecules are deprotonated. Meaning, if you go back to this and look at the actual reaction, I want more than, so if I had equal amounts of both of these, right? So if 0.75, if I started with 0.75 of this, then 0.375 would be half, like equal amounts are present. But I don't want equal amounts. I want more of my base. So if you think about it, if I have equal amounts of both of these, then I have an ideal buffer because I've got equal amounts of my weak acid and my weak base. So if I have equal amounts of these, that is my half equivalence point. That is when pH equals your pKa. So I'm basically saying, hey, I don't want to be right at my half equivalence point. I want to be past my half equivalence point. All right, so what pHs would that be at? Well, since my Ka value is given to me as 1.12 times 10 to the negative 10th, if I take the negative log of that, 9.95, that is the pH that I want, but I want to be above that because this is when I have equal amounts of my weak acid, weak base. I want even more weak base, which means the pH will be higher. So I need to circle all of the values that are going to be higher than a pH of 9.95 because then that would tell me I have more base than I have acid. And so the pH I would want to go for, I would want to circle 10 and all of the ones above 10. So just as a quick review, okay, if I have equal amounts of these two, that is when I'm at my half equivalence point where pH equals pKa. But because it said I want more than 50% to be deprotonated, I need to be beyond my half equivalence point, meaning I want my pH to be above the 9.95 that I'd calculated previously.